Electrical grounding is a critical aspect of electrical safety, primarily intended to prevent electrical shock and minimize the risk of equipment damage. Proper grounding establishes a low-resistance pathway that allows excess electrical current to flow safely to the earth. This prevents dangerous voltage from accumulating on equipment, enclosures, and other conductive surfaces, thereby protecting personnel from potential electrical hazards. Grounding is not just about safety, it also plays a role in the proper operation of electrical systems, ensuring that overcurrent protection devices, such as circuit breakers and fuses, function correctly to clear faults. The concept of grounding involves creating an intentional connection between the electrical system and the earth. This connection provides a reference point of 0 volts potential, meaning that the grounded components are at the same electrical potential as the earth. When a fault occurs, such as a live wire coming into contact with a grounded metal enclosure, the low resistance path to ground allows a large current to flow. This high current trips the circuit breaker or blows the fuse, quickly disconnecting the circuit and preventing a sustained electrical hazard. The effectiveness of a grounding system depends on several factors. Firstly, the quality of the grounding electrode, which is typically a metal rod or plate buried in the earth. The grounding electrode should be made of a corrosion-resistant material such as copper or galvanized steel and should be installed in an area with good soil conductivity. Secondly, the grounding conductor, which connects the electrical system to the grounding electrode, must be of adequate size to carry the maximum fault current. The size of the grounding conductor is determined by the size of the circuit conductors, as specified in electrical codes such as the National Electrical Code, or NEC. Thirdly, the bonding of all metal enclosures, equipment, and non-current carrying conductive parts is crucial to ensure that they are all at the same electrical potential. Bonding involves connecting these parts together with a low-impedance conductor, creating a common ground reference. There are different types of grounding systems, including firstly, the equipment grounding system, which provides a path for fault current to return to the source, tripping the overcurrent protection device. Secondly, the system grounding, which grounds the neutral point of the electrical supply, providing a stable voltage reference and limiting voltage surges. Thirdly, the static grounding, which dissipates static electricity, preventing sparks and potential ignition in hazardous locations. Proper grounding also minimizes the effects of electromagnetic interference, or EMI, on sensitive electronic equipment. EMI can cause malfunctions, data errors, and reduce performance. By providing a low impedance path for unwanted electrical noise to flow to ground, grounding helps to reduce EMI and improve the reliability of electronic systems. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections should be checked for corrosion, looseness, and damage. The resistance of the grounding electrode should be measured periodically to verify that it is within acceptable limits. Any deficiencies should be corrected promptly to maintain the integrity of the grounding system. In addition to preventing electrical shock and equipment damage, proper grounding also helps to protect against lightning strikes. A properly grounded lightning protection system provides a safe path for lightning current to flow to the earth, minimizing the risk of fire and structural damage. The lightning protection system typically includes air terminals, down conductors, and a grounding electrode system. Grounding is an essential component of electrical safety, and it is crucial to ensure that all electrical systems are properly grounded. Improper grounding can create dangerous conditions that can lead to electrical shock, fire, and equipment damage. Therefore, it is important to follow all applicable electrical codes and standards when installing and maintaining grounding systems. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. The NEC specifies the types of grounding electrodes that are permitted, the size of grounding conductors, and the methods for bonding metal enclosures and equipment. It is important to consult the NEC and other applicable standards when designing and installing grounding systems to ensure compliance with all safety requirements. Grounding is a fundamental principle of electrical safety, and it is essential for protecting people and property from the hazards of electricity. By providing a low resistance path for fault current to flow to ground, Grounding prevents dangerous voltage from accumulating on equipment and enclosures, minimizing the risk of electrical shock and equipment damage. To further elaborate on the importance of grounding, let's consider some specific scenarios. In a residential setting, a faulty appliance such as a washing machine or refrigerator can develop a short circuit, causing the metal enclosure to become energized. If the appliance is properly grounded, the fault current will flow through the grounding conductor back to the electrical panel, tripping the circuit breaker and cutting off the power. This prevents anyone who touches the appliance from receiving an electrical shock. Without proper grounding, the metal enclosure could remain energized, posing a significant shock hazard. In an industrial setting, the consequences of improper grounding can be even more severe. Large machinery and equipment often operate at high voltages and currents. If a fault occurs in one of these machines, the resulting fault current can be very high, potentially causing significant damage to equipment and creating a serious safety hazard. Proper grounding provides a low impedance path for the fault current to flow to ground, minimizing the voltage rise on metal enclosures and preventing electrical shock. Additionally, grounding helps to protect sensitive electronic equipment from damage due to voltage surges and transients. In addition to the NEC, other standards and guidelines provide information on grounding and bonding. The Institute of Electrical and Electronics Engineers, or IEE, publishes standards on grounding and bonding for various applications, including power systems, telecommunications systems, and electronic equipment. These standards provide detailed recommendations on grounding practices to ensure safety and performance. Proper grounding is not a one-time installation, it requires ongoing maintenance and inspection. Grounding connections can corrode over time, reducing their effectiveness. It is important to periodically inspect grounding connections and clean or replace them as needed. The resistance of the grounding electrode should also be measured periodically to ensure that it is within acceptable limits. High resistance can indicate a problem with the grounding electrode or the soil conductivity. In some cases, it may be necessary to install additional grounding electrodes to improve the grounding system. Grounding is a complex topic, and it is important to consult with qualified electrical professionals when designing and installing grounding systems. Electrical contractors, engineers, and inspectors can provide guidance on grounding practices and ensure that all applicable codes and standards are followed. Proper grounding is an investment in safety and reliability. It protects people from electrical shock, prevents equipment damage, and minimizes the risk of fire. By following proper grounding practices, it is possible to create a safe and reliable electrical environment. The principles of grounding extend beyond simple electrical safety and are crucial in protecting sensitive electronic equipment from damage and ensuring the reliable operation of electrical systems. Grounding provides a stable reference point for voltage, minimizing the effects of electrical noise and interference. This is particularly important in environments with sensitive electronic equipment, such as hospitals, laboratories, and data centers. Without proper grounding, electronic equipment can experience malfunctions, data errors, and reduced performance. Furthermore, grounding is essential for protecting against electrostatic discharge, or ESD. ESD is the sudden flow of electricity between two electrically charged objects. It can damage sensitive electronic components, causing them to fail prematurely. Proper grounding provides a path for static electricity to dissipate safely, preventing ESD damage. In addition to equipment grounding, system grounding plays a vital role in the overall performance of an electrical system. System grounding involves grounding the neutral point of the electrical supply, providing a stable voltage reference and limiting voltage surges. This is particularly important in three-phase power systems, where unbalanced loads can cause voltage fluctuations. System grounding helps to stabilize the voltage and prevent damage to equipment. The selection of the appropriate grounding method depends on the specific application and the characteristics of the electrical system. Common grounding methods include solid grounding, impedance grounding, and ungrounded systems. Solid grounding provides a direct connection between the neutral point and ground, resulting in a low impedance path for fault current. Impedance grounding uses a resistor or reactor to limit the fault current, reducing the stress on equipment and minimizing the risk of ground faults. Ungrounded systems do not have a direct connection to ground, but they can still provide a degree of protection against electrical shock. Each grounding method has its advantages and disadvantages, and the selection of the appropriate method depends on the specific requirements of the application. Grounding is not just a theoretical concept, it is a practical necessity that must be implemented correctly to ensure safety and performance. Proper grounding requires careful attention to detail and adherence to applicable codes and standards. It is important to use high-quality grounding materials and to install them correctly. Grounding connections should be tight and corrosion-resistant, and grounding conductors should be properly sized to carry the maximum fault current. In addition to proper installation, grounding systems require ongoing maintenance and inspection. Grounding connections should be checked periodically for corrosion, looseness, and damage. The resistance of the grounding electrode should also be measured periodically to ensure that it is within acceptable limits. Any deficiencies should be corrected promptly to maintain the integrity of the grounding system. Grounding is an essential component of electrical safety and reliability. It protects people from electrical shock, prevents equipment damage, and minimizes the risk of fire. By following proper grounding practices, it is possible to create a safe and reliable electrical environment. The importance of grounding cannot be overstated. It is a fundamental principle of electrical safety and a critical component of any electrical system. Whether it is a residential wiring system, an industrial power distribution network, or a sensitive electronic device, proper grounding is essential for protecting people and property from the hazards of electricity. In conclusion, ensuring proper connections for an electrical grounding system is paramount for safety. It establishes a low-resistance path for excess current, mitigating the risk of electrical shock and preventing equipment damage. By adhering to electrical codes, maintaining grounding systems, and understanding the principles of grounding, we can create safer electrical environments for everyone.